Welcome you all to this course on defects in materials. Okay. Yesterday we have covered some aspects of point defects, especially what are the different types of point defects which we have, how to find out the concentration of the point defects which are present in the sample. Then briefly mentioned about how to find out the experimental identification of the concentration of the defects and the formation energy, especially using one experiment for vacancies. So there are many methods which are available to find out the defect concentration. One of them is using thermal expansion and XRD combined. This is what we discussed yesterday. Then another is positron annihilation technique. The next, then resistivity, stroke conductivity. Let us start with because since we have already mentioned, I will not repeat that again about thermal expansion and X-ray diffraction. But the basic philosophy in this experiment is that whenever a material expands, the thermal expansion studies we do it, it is not only that because of the lattice vibration there is an anelastic expansion. In addition to it, when defects are being produced in the lattice, especially vacancies, atoms are removed from the sample surface and they from the inside and they come to a surface. So there is a volume increase is going to be there. So the thermal expansion takes care of two parts of it. One is the expansion of the perfect lattice plus the defects which are there, which also contribution due to them. And when these defects are being present, when they do relax, they give rise to some contraction or expansion of the lattice locally. So this can be measured using X-ray diffraction. If both these informations are available, using combination of thermal expansion and X-ray diffraction, we can get information about the equilibrium concentration of vacancies which are there. If we find out that, get that information for different temperatures, then plotting this concentration versus 1 by T, we can get information about the vacancy concentration in the material. That is because N by N equals exponential minus EF by KT, correct? This is what essentially we use it to find out the concentration of vacancies. Now, another powerful technique which is there with which we can find out the concentration of vacancy is positron annihilation technique. In a positron, so you might have all studied about what are positrons. Positrons are nothing but having the same mass as that of electron and a charge which is positive, right? And in fact, this is the first example of an antimatter which is being discovered. And how are they produced? When radioactive decay takes place of beta plus decay, positrons are produced. That is, in many radioactive decay, electrons are emitted and the atom undergoes a change to another element. Similar to that, if it emits a positron, then what is essentially is going to happen is that the total number of proton plus nucleus, proton plus neutrons remains that same, but the positive charge gets reduced by 1. Like for example, if we take sodium, sodium will transform to neon, keeping the proton plus neutron number the same. Okay. In this process, when positrons are emitted, in addition to the positrons, in many cases gamma rays are also emitted to take care of this mass defect. Okay. These gamma rays are emitted simultaneously when a positron is also emitted. If we can find out this time at which it is being emitted and find out the time which is taken for this positron to enter into a sample, and if it interacts with an electron and it gets annihilated, then two gamma rays are emitted. But these gamma rays have got a fixed energy, okay, which is of 0.511. So the energy of the gamma rays which are emitted is generally 0.511 MeV energy with which two gamma rays will come. That is, this is the rest mass energy of the proton, positron and the electron. Okay. When they combine together, okay. So this is clear. And the gamma ray which is emitted from the radioactive decay, that will have a very high value. For example, in the case of sodium, it's about 1.27 MeV is the energy of the gamma ray. Okay. So the initial signal that a positron has been generated is, as soon as it is generated, a gamma ray is also generated. You detect that gamma ray. Then wait for the next gamma ray with that energy 0.511 MeV to be detected. The time difference between them tells the time which has taken for the positron to get annihilated in the sample. Okay. Suppose the material contains some defects. Possibly the positron has to get trapped in that defect. It has to wait for a longer period of time, okay, before an annihilation takes place with an interaction with an electron. Okay. So that time difference, okay, is what gives an indication about, okay, the nature of the defect which is present there. Generally, the vacancy type of the defects on which the positron where it stays for a longer period of time. Okay. This we will talk about it later. And this is an extremely sensitive technique, okay, and very accurate to identify the type of defects. That is, suppose the defect is going to be a monovacancy, or it's a divacancy, or a trivacancy, or if it is a void, okay, or many type of structural defects like dislocations. Each of them will have a characteristic time which it takes, okay, for the defect to stay there. Identifying that time which it takes, delay time which it takes for the positron to annihilate, we can get information about the nature of the defect. And if you look at the peak height, it will always give information about the number of counts which are coming, okay, with that particular delay time. We can immediately talk about what is going to be the concentration of the defect. This is the philosophy in almost all the spectroscopy techniques. Okay. And not only that, vacancy concentration as low as 1 in 10 to the power of minus, that is 1 in 10 to the power of 7, okay, could be easily detected using positron annihilation technique. Okay. As I mentioned earlier, the vacancy concentration even at melting point is of the order of 10 to the power of minus 4, 10 to the power of minus 3 to minus 4. So 3 orders difference in vacancy concentration could be detected. Okay. Let us just talk about some of the experimental techniques which are used, so that one is aware of how this technique could be used to get the, and this technique gives an absolute concentration of the vacancy concentration which we can detect. Okay. What are the sources of isotopes? One is sodium, okay, that is particular isotope is important, the number 22 sodium, 64 copper and 58 cobalt, this could be used, out of which the sodium is the one, okay, which has got a gamma with the smallest energy which is coming out of the sample surface. Okay. This reaction, when it takes place, if you look at it, there is a direct transition which takes place, emission of positron without any gamma ray emission. Okay, that's about 0.1%. And there is another one which is where we have a gamma ray is also emitted, okay, simultaneously. This is the transition which is of interest, okay, because we are able to simultaneously to find out that information that a gamma ray is emitted. When is it emitted? Okay, that when the positron is emitted, that information is given by the simultaneous emission of the gamma ray. Okay, if you detect the gamma ray with this particular energy, we know that a positron also has been emitted. Okay. Now, what is the source? This is a source which is there. You have a sample. Okay. In the sample, when the gamma ray enters, and gamma ray has got a very high energy, so it travels through the sample, gets thermalized. Okay. Normally about close to 100 micron is the depth which it travels. Okay. And then when it thermalizes and its energy gets reduced, it has to get annihilated finally. Correct. So any material, if you take of it, metallic material, they contains ions which are located at different positions, okay, at a and also electrons which are there distributed uniformly throughout that sample. Okay. When it gets thermalized, there's a chance that this electron, a positron will interact with that electron, get annihilated, and a gamma ray will be generated. Okay. Suppose you assume a case where there are no defects which are present in the material. Then it takes some specific time for the gamma ray to get annihilated, because it's being decided by the density of the electron distribution in the sample. Okay. This is what it is going to happen. Suppose a defect is there. The region where the defect is present, like here in this case if you see it, okay, when there is no defect, irrespective of whichever be the site it moves and reaches, it does not matter whether this point or this point, okay, it is going to take almost an identical delay time which is going to be there, okay, because the density of electron is going to be the same almost in all the regions. If there is a defect which is being present, then you can see that this is the, what is defect? This is a region where otherwise there has been a positive ion which was there. When the positive ion has been removed, okay, the electron distribution is mostly in these regions in between, and in this region the electron distribution, when the defect is there, some electrons will try to come, but the density is going to be very small. So if a positron comes and sits here, the time which it takes to annihilate depends upon the arrival of the electron, or it is related to the density of electron which is going to be there in that region. This will decide, suppose it's two defects which are there going to be there, or more defects, then the time it takes for electrons to come and interact with positron and annihilate is going to take a longer period of time. Logically one can think that way. Okay. So this will decide the, and using this delay time we can try to find out also is that how much of how much the concentration of the defects are, and also the nature of the defect, okay, both could be identified. So what we try to do is that try to find out, then there are many other techniques. This is what is called as a positron lifetime technique. So we are trying to find out what is the lifetime of a positron, okay, depending upon the defect, the lifetime could be large or small. Okay. Essentially the setup which consists of two detectors which will be there. One detector detects essentially the positron with which is emitted from the source, okay, with a high energy. The other one, one detector detects the gamma ray which is emitted from the source along with the positron. The other one finds out the gamma ray which with the 0.511 ME which is being detected. So the time delay between these two is going to give you information about, okay, the lifetime of the positron, or from that we can get information about the nature of the defect. Okay. Finally, what we will be doing it is that this lifetime which is being measured will be plotted the time which it takes, okay, versus the count. Okay. If you look here, there is one plot, this plot which corresponds to a sample which has been well annealed. Okay. This is how the positron annihilation lifetime looks like, because there will be some scatter will always be there. It is not going to take place at one, right? Whenever a positron gets trapped in a vacant site, okay, in a defect site, okay, the electron coming and annihilating with it, it's an average lifetime which we talk about, but there will be some distribution which will be there. So this is an example which I have taken from a literature. It's on the it's in molybdenum. Okay, in molybdenum, okay, a sample which has been well annealed. This is how the lifetime measurement gives that plot. Okay, when this is irradiated with injected with helium ions with some clusters, okay, some defects are also getting attached to it. Now you can see that on the right hand side, the shape of this plot, there is a change, the slope changes, correct. And when it is irradiated with neutrons and where a lot of voids are produced, by other techniques we can identify the voids, that voids have been produced, you can see that the slope has changed. Okay. So the difference, if you see between these two, this one, that is going to get information about the difference in lifetime which is going to be there. Okay. From these plots we can get information about the type of defects which are present, okay, and their concentration. This is another plot where what is being done is that only for the, suppose a defect contains, okay, number of vacancies. If it contains about 5, 10, this is what it's being shown, what is going to be the lifetime, how it changes with the number of defects being present. And in this particular case where there are a lot of clusters are there, where there are no helium ions are associated with it, then you can see that the increasing the number of vacancies, okay, in that region, you can immediately notice that lifetime increases considerably. Okay. So from this you can understand that this itself could be used as a technique to find out the concentration of the vacancies. Suppose you assume that some interstitial or some other element is going to be present. Then what's going to happen is that there, at the site when it is going to be there, at an interstitial site, the electron concentration is going to increase, right? So it will not make much of it. So the positron will get annihilated much faster. So that way it is extremely sensitive to vacancy type of defects present in the material. Okay. And with this method we can find out absolute concentration of vacancy in the sample. Okay.
So from the time, how are you determining the concentration?
Which one?
We know the time lapse.
The time lapse tells you here that for each time lapse how many counts are coming, we are looking at it. Suppose the defect concentration is less, okay, then what will happen is that this plot, when you look at it, either it could be one which is coming like this. If the concentration of defect is going to be there, it will be coming like this, correct? So for the same concentration, this height, if you try to look at it, the counts for the same time is going to be different, correct? That is dependent upon the vacancy, the defect concentration. So from this we can get both the information. If you look at this plot, it's the log of count, okay, with a particular time constant, that is lifetime. Okay. Looking at this, we can get that information about this is some defect which is in an annealed sample. If some defect is being introduced into it, we can find out that how much is the defect which is present in this sample, correct? Because the count has increased on that. Okay. That way we get information about that. Okay. Okay. The another technique which also can be used to get information about the defect concentration is electrical resistivity or conductivity measurements. Okay. Especially in metallic samples, electrical resistivity has been used to get information about, okay, point defect concentration as well as the migration energy, not only point defect concentration, formation energy as well as the migration energy of defects, we could get that information. Okay. We know that resistance, if we look at it, okay, if you measure the resistance of a material at any particular temperature is a function of two terms. One, the resistance, the lattice resistance, plus the resistance, the contribution to resistance which is coming from the defects which are present in the material. But the defects could be impurities, dislocations, okay, various types of things like grain boundaries, all these things could be there, plus vacancies could be there, correct? So, all of them will contribute to resistivity. Okay. If we take a sample where we assume that the concentration of impurities have been reduced to a very small value, okay, assume highly pure material, and by some means or the other the zinc concentration is kept that same, then whatever is the defect which is contribute to resistivity change will be only due to the vacancy. That is the assumption on which we go about the experiment, because some precautions have to be taken in this case to control the defect concentration in the material. That I will talk about little bit later, okay, with which we can find out the vacancy concentration. And generally the contribution to resistivity from the lattice vibration is going to be very high. So, if you have to reduce it, you do the experiment at very low temperatures. So, by lowering the temperature, what are we trying to do? Okay. The contribution due to lattice vibration is reduced. Now, the major contribution is coming only from the defects which are present in the material. Okay. Okay, let us take a sample, okay, which is a very well annealed sample, where the concentration of, we assume that the vacancies is very small. Okay. You measure the concentration, that is denoted by rho Q, okay, that determines the concentration at a temperature which is a low temperature. Then that same sample, if I heat it at a very high temperature and then quench it, when I quench it, what is going to happen is that all the vacancies should be retained. Here we make an assumption that in reality what happens when you quench it fast, some of the vacancies condense to form dislocation loops, vacancy loops and all these things, and they get annihilated. We make the assumption that the same concentration of vacancy is retained. Okay, that is the first assumption which we make it. Then the difference between the resistivity measured at a particular temperature between a well annealed sample, okay, and the sample which has been quenched, okay, that tells the resistivity change. Okay, that is proportional to the number of defects which are present in the material, correct? We carry out this experiment by taking the sample to different temperatures like T1, T2, T3 like this. Different temperatures we take it, allow the vacancy concentration to equilibrate and quench it to the very low temperature and measure the resistivity. And we know the resistivity which has been measured in the well annealed sample. That way the resistivity change corresponding to vacancy concentration at different temperatures, we can get that information. Okay. That vacancy concentration, we know that right from the beginning when we have derived an expression for the equilibrium concentration of vacancy, is that this delta n by n equals exponential minus EF by KT, correct? Or this itself will turn out to be the resistivity change is proportional to delta n. So, we get an expression connecting delta n. So, if we plot delta n versus 1 by T, we can get information about the formation energy of the vacancy. Is it clear? Okay. Now, The same electrical resistivity measurement could be used to find out the migration energy of the defect also. Okay? Because in this experiment what we have done it is that in the earlier experiment which I just now mentioned is that we have allowed the equilibrium concentration of vacancy to be present in the sample, and we have found out what is the contribution due to that to the resistivity, correct? And then plotting the resistivity versus 1 by T, we are able to find out the only energy of formation. Suppose we anneal the sample at a particular temperature where the vacancies are mobile. Then what will happen is that no more vacancies are added, but whatever the vacancies are there, we are trying to allow the vacancy concentration to equilibrate, the vacancies reaching different sinks and getting annihilated. That means that now the vacancy mobility is what we are looking at it. So if we study the mobility of vacancies, then we can get information about the migration energy, right? So what we have to do is that take a sample, keep it at high temperature, create some equilibrium concentration of vacancies, lower it to a temperature where you measure it. Okay, you have got information about the how much is the resistivity change which is going to be there. Now you the same sample rise it to a slightly higher temperature. Okay, then anneal it for different periods of time at a particular temperature, and then try to find out what is going to be the vacancy concentration in the sample. As we anneal, the concentration of vacancies will gradually get reduced. Okay, note down that is anneal it for a particular period of time, bring it to the lower temperature, measure the resistivity, again take it to the high temperature, anneal it for some more time. That way you get how the vacancy concentration is going to be getting reduced. Okay, or the how resistivity is changing, that information we collected. If we try to plot this resistivity rho with respect to an initial resistivity rho 0, which corresponds to in the quenched sample, the plot always will be an exponential type of a plot. You know that this exponential type of plot comes because the number of defects which are available to move to the sink is getting continuously reduced. So the rate at which the defects are getting eliminated from the sample is proportional to the number which is present. That if we try to plot it, it always be an exponential plot. That is what essentially we get that information. And this plot, what is to is that we call it as the relaxation time. That's the time which it takes for the concentration of the defect to come to 1 by E of the original value. Okay. So this experiment, if we carried it out at one particular temperature, we get some defect concentration. Okay. How it varies the resistivity. If you try to look at this plot, we start initially from here, it decreases like this. Now at this this is done at a temperature T1. Now if I raise the temperature or lower the temperature, then a relaxation time will be different because the rate at which the atoms are going to jump. So then I will be getting another plot corresponding to it, correct? So if we do this experiment for different annealing time, this is an isothermal experiment because all annealing is carried out at the same, one is at one particular temperature, this is T1, this is T2. Okay. From this experiment, these two plots, we can find out the TO1 and TO2, correct? Any of these plots if we have, we can find out the slope. Okay. And this TO depends upon what is it? The migration energy, the rate at which the defects are jumping and reaching the finally getting annihilated at some of the defects which are being present in the sample. So here when we change the temperature in this experiment, okay, if the the zinc concentration itself changes, then what will happen is that the rate at which the defects are getting annihilated, that will change. So that is why this experiment is performed on a sample which has been initially quenched, and we do annealing at temperatures where the defect concentration or the zinc concentration does not change. So if the zinc concentration remains the same, that does not that factor corresponding to that in the resistivity changes remains constant. So now whatever is the change which is occurring is only due to the jump rate of the vacancy from one side to the another side. So we can write two expressions, one corresponding to tau, one corresponding to this part of the curve, another to this part of the curve. We can find out the relaxation time. Okay. If you try to plot this is the sort of a plot which will happen versus time. If you take it's a semi-log plot, okay, and the temperatures which we have taken is tau 1 and tau 2. At the point at which we have changed over from one temperature to another temperature, okay, at this the ratio of tau 1 to tau 2 should be equal to this sort of an expression will come. This expression one can derive it from this expression. We can write it tau 1 equals this 1 by T1, okay, another tau 2, you take the ratio. So from this expression we get, or from this plot, okay, when we have tau 1 versus tau 2, or this is the same as equivalent to the rate of change of the resistivity plot, okay, the slope of it, we can find out the migration energy, right. This is how using resistivity migration energy change could be measured. Any questions? Is it all right? It's not clear. Okay. Is this clear? This tau is essentially equal some constant Em by, this is clear. Okay. If I do an experiment at T1, this will be tau 1. If I do an experiment at T2, this will be T2, correct? If I take the ratio of this, what it will happen? We get this expression, okay? From a plot like this, okay, from the curvature of the plot, we can find out tau 1 and tau 2, okay? We know the temperature at which we have done it.
No, sir, but the curvature for that plot, for example, temperature is fixed, but on the x-axis.
Which one? No, here it is, this is with respect to time.
Yeah, so you need to fix at what time you are taking that curvature.
Which one?
You need to fix the time at which you are taking the derivative. The del rho by del t.
Yeah. No, here that is why we assume that if we take two different samples, the tau depends upon what all factors. Okay? The tau depends upon a factor which is essentially what all factors tau depend on? Tau depend upon one, the length which it has to travel, the defect to reach the sink, and a constant beta, and the diffusivity. Diffusivity is at a particular temperature, it is being fixed. Okay? So essentially, irrespective of what the concentration, the rate at which it is going to jump, if the sink distribution is fixed, okay, then L is going to be fixed. Only the diffusivity determines how the tau is getting affected. Irrespective.
From that curve,
Yeah.
delta rho appears to be a nonlinear function of time.
Yes, because this is an exponential function.
But when we take the derivative, right,
Yeah,
because we are taking the ratio of the derivatives to arrive at tau 2 by tau 1.
yeah.
So for that, I need to know where I am taking the derivative.
See, if you take a derivative of this expression, what will happen? Delta 0 is a constant. You take it by d by dt. Minus 1 by 2 into exponential of minus t by 2, correct? So this factor essentially is that this itself, we can plot it. Now from the curve, whatever be the value which you take it, okay, this will be what it will turn out to be. If you take a log of this one, okay, then you understand that this is quite simple. Eh? Where it will be cutting it, you get this tau, correct? It's clear? Okay. This way you can immediately find out what the tau is. Okay. That's why I said that. So this way it's a very neat experiment with which we can find out the migration energy. So using resistivity, two types of experiment on the same sample, okay, we can find out the formation energy as well as the migration energy of the defect, and this total energy is the energy which we use in most of the diffusion experiments to tell that this is what the activation energy, correct, for diffusion. Okay. The values of migration and formation energy which has been calculated for different types of defects are given here. Okay. It is taken from the literature, and you can make out that here that V1 and V2 what it corresponds to is one, V1 corresponds to mono vacancy, V2 corresponds to a di vacancy. Okay. What are the activation energies? Okay. With using this information, one can find out what is going to be the self diffusion of vacancies in the material. That requires both the energy, not what is the energy which is required for a vacancy to be formed, what is required, the energy which is required for the vacancies to move. Then only we will get information about the self diffusion, the energy which is required for self diffusion of vacancies to take place. That is what the information which is provided in this table. Okay. This information is very much necessary when diffusion has to take place, because diffusion is essentially assisted by vacancies. Okay. This is the same information which is being provided in this view graph also, but what is essentially important is that in many cases, okay, when we consider a defect which is mobile, okay, in a pure metal it is very easy because it's the adjacent atoms are going to be all the same identical type of an atom. Quite often in an alloy or a material which contains some impurities, it can so happen that in a region, that is if we consider a defect which is being present, this atom could be another type of an atom. If it is a different type of an atom, assume that it has got a larger size. Then if it remains very close to a vacancy, okay, it is able to accommodate part of the strain. Then if it has to move, the whole complex has to move, not the vacancy alone. Okay. This is one thing which is going to happen. In fact, this property has been used in many cases, especially in radiation damage situation, to control the vacancy concentration in the material. That means that suppose we have generated some vacancy, these vacancies agglomerate together to form voids. That means the vacancy should move. If you introduce some impurity into the material so that the vacancy forms a complex with it, now the rate at which the vacancy is going to move is getting reduced drastically. So as a function of time, if you look at it, the concentration of the agglomeration of vacancies to voids could be reduced considerably. Okay. Especially in materials which has to be used for structural materials in nuclear applications. Okay. That's especially in stainless steels. Some titanium is being added because the titanium forms some complexes with vacancy, okay, so that it can reduce this vacancy mobility. Okay. No, so far what we talked about is vacancy concentration in essentially metals. Suppose we consider vacancy concentration in ionic materials. Okay. The material, okay. The resistivity in ionic material or the conductivity in ionic material does not depend upon the electron concentration, it all depends upon the charge carriers, which are the ions which has to move. Okay. And that is what is going to control the concentration. And another important fact which has to consider in ionic material is that we have to maintain the charge neutrality always, right. When you have to maintain the charge neutrality, if a cation vacancy is going to be there, some value, then the anion vacancy also has to be of the same value. This is what we call as a Schottky defect, correct. Then when they have to migrate, a cation vacancy will move from one cation site to another cation site, and that is how they migrate. Similarly, anion also will move from an anion, one anion site to another anion site. Okay. So essentially this we can consider it as something like the two types of sublattices are there. One lattice is made up of all anions, another lattice is made up of cations. Okay. So from one anion site to another anion site, if you have to move, it has to go across the sites in between. There are some cations will be there through which it has to push through, but it will always go to a site which is from one anion to another anion only. The same is true for cations as well. Okay. The expression for equilibrium concentration of cations and anions, okay, this derivation is similar to what we have derived for vacancy concentration in metallic system. Okay. Only thing which you have to consider it is that the total number of lattice sites, if it is n in for cations, another n is going to be for anions, that is if it is. So totally 2n will be the total number of sites, okay, and the defect concentration also, if it is n in anion sites, n in cation sites, so that will be the total 2n will be the anion and the cation site. Okay. Then if you try to find out the ratio of in any particular site anion concentration, okay, then it is given by this expression. This expression derivation is very similar, that is you write an expression for this anions alone, okay, I will put this, and similarly another expression for cations we can write it, and the product of it, this is going to give you, okay, the concentration of the defects, correct. With that one can derive at this expression. Similarly, we mentioned earlier that we can have a Frankel type of a defect where one vacancy is created, okay, and of an anion, and the anion sits at an interstitial position. Okay. There also the concentration can be written by an expression similar to that. Okay. So essentially, if you look at the conductivity, okay, is this clear? Now if you look at the conductivity, if you apply a voltage, okay, positive and the negative voltage, if we connect it, all the negative ions will move towards this side, correct. Positive ions will move towards this side, correct. The net current is the sum of both, but when an electron we consider, they move very fast, whereas here it is an ion which has a larger size, so its movement is rather slow. So the rate at which the current flows, because current is nothing but rate of change of flow of charge, okay, dq by dt. So that depends upon the mobility with which these ions are drifting from one end to the other end. So if you look at the, for example, if you take sodium chloride, okay, in an ionic material, both the sodium ion also will move, chlorine ion also will move, correct? So the conductivity is nothing but sigma equals N into E that is both the charge movement. But normally what has been seen in many of this material, okay, the size of the anion is going to be very large, okay, cation size is small. So cation moves much faster compared to that of the anion, mobility is high. Because of that, essentially the conductivity is controlled by cation mobility. In that case, this expression will reduce to one which is nothing but sigma equals, only because this term will be absent, only this Ne into mu plus, okay. Suppose we measure a sample, okay, measure its conductivity, okay, as a function of that cation as a time, okay, and plot the conductivity versus 1 by T, then we can get information about the formation energy, correct? This is what we can get information. But since here the cation moves rather slowly, not only about the formation energy, it essentially gives the diffusion of the ion itself, that information which it comes. Okay. That is essentially, it will be now formation plus the mobility, because the rate at which it moves is not like that of an electron. So the mobility information also comes into the picture. Okay. This will become clear when we go along. Okay. If you look at the impurity concentration, because no material is pure material, okay, some impurity will be present. Okay. The impurity in most of this ionic material could be, okay, another ion which has been added, which has got a different valence state. Okay. Let us consider an example. Cadmium chloride is added to sodium chloride, or it could be a calcium chloride. Okay. Then what's going to happen is that the site which if a sodium atom is replaced, the sodium ion is replaced and the cation site, and it is occupied by a cadmium 2 plus. Okay. That means to maintain the charge balance, one sodium ion has been removed from another site, right? Assume that in this a divalent ion is there. So maybe in an adjacent site, the vacancy is created so that the charge neutrality is being maintained, correct? Then what is going to happen? Yeah.
The probability of the defect being closer to the charge is higher. So, for example, the vacancy would be closer to this defect.
Vacancy will be closer to the defect. If it is very far away, then what's going to happen is that the space charge effect is going to come into the picture. So generally they assume to be closer to it. Generally they prefer to be closer to the site. But this is also depending upon the temperature. Okay. So that is what we will come talk about it later. Okay. So essentially what is going to happen is that if a defect is being present in the sample, okay, some impurity concentration is there. At a high temperature, if we take that sample, at high temperature the concentration of the impurity which is added is very small. So, the most of the concentration of the defect is essentially due to Schottky defects, right. So, if you look at the conductivity will have two parts which will come, okay, because the Schottky defect, when we talk about it, it means that the concentration of the anion vacancy and the concentration of the cation vacancies are the same. By the addition of the impurity into the system, we have generated, depending upon the concentration, if Ni is the concentration of the impurity which we have added, corresponding to that much number of cation vacancy is also introduced. So, the cation vacancy is always now more than that of the anion vacancy in the material. Okay. So, the contribution to conductivity is going to come from two terms, one due to the cation vacancy which is generated by the defects, generated by the impurity, and another is due to a defect which is created in the lattice. Okay. So, the conductivity will be turn out to be this sort of an expression. Suppose we look at the conductivity at very low temperature, then what will happen? At low temperatures, the Schottky defects are going to be very small. Okay. Then the impurity concentration is the only one which is going to decide, okay, how much is going to be the cation vacancy in the material, correct? And mobility depends upon the conductivity. Okay. If we do a plot, okay, conductivity versus 1 by T, okay, then this is the nature of the plot which we normally get it. Here this one part corresponds to a high temperature where the concentration of the defects is essentially coming from Schottky defects, okay. And in that, if you look at the slope of this plot, this corresponds to, okay, the formation energy of the cation and the anion, okay, and also because since these ions move with different mobility, the mobility of the ion also comes into the picture. If we look at the lower temperatures, there the concentration of vacancy is decided by, the concentration of the defect is decided by the concentration of the impurity which we have added, correct. At different temperatures the mobility will change, okay. That is why we get different conductivity, correct. Now if you look at the slope here, the slope at this curve corresponds to only the migration energy. That is what we have plotted here is essentially 1 by T versus rho conductivity, correct. And this also so if you try to plot it, this essentially gives, is essentially proportional to correct. So, this term is going to correspond to, from the slope you will be able to get, this is the way the conductivity is going to change, correct. Because essentially what we are finding out the defect concentration at various temperatures, okay, and at lower temperatures the defect concentration is fixed. So, only the mobility decides how the conductivity is going to vary. So, that gives information only about the migration, because the concentration of the defects, when it is constant, this part will not come into the picture. Okay. So, using this sort of a plot, we can get information about both the migration energy as well as the formation energy. All this information we can get it. Quite often what happens is that this is not a straight line, especially the lower part. Why it is not a straight line? As you pointed out earlier, that is, this defect could form a complex with the defect, that impurity, that is the divalent impurity and the vacancy forms a complex which are seem to be close by, and they would try to prefer to move together. Okay. If that happens, okay, those complexes will change the behavior of the plot and it will be curved. Okay. That's what in reality in many situations. Generally, especially at very low temperatures. At high temperatures, what can happen is that the defect can still be mobile. Okay. This effect will not be seen, but at low temperatures, this is very prominent. Okay. Now, what we will do is that we will break here, okay, then talk about how impurity concentrates. So, what we have considered so far, a vacancy concentration in metallic material as well as in ionic materials, how to determine, we have discussed, okay, using various techniques. One is thermal expansion and X-ray diffraction, another is resistivity technique, and another is using positron annihilation technique. We will stop here now.